Hi everyone, let's solve today's daily challenge, that is check completeness of a binary tree. So in this question we are given the root of a binary tree and we need to determine if it is a complete binary tree. Right, so here the definition of a complete binary tree is given. Right, so let's first see what a complete binary tree is. First of all, it is like whatever tree is given to us, it should be binary. So let's draw a tree here. So now this is the binary tree, correct? Yes, it is a binary tree. But for it to be complete, all its levels should be filled, right? All the levels should be filled except for the last level, right? So here if we see the first level, it is full. The second level, it is full. But if you see the third level, it is not full, right? And it is not the last level. It is the third level. The last level is fourth level, but the third level is not full. So that means this is not a complete binary tree. Now, what is the second condition for a tree to be complete binary tree? Now let's say we are given a tree something like this. We have this tree. So we said except for the last level, all of the other levels should be filled. So here you can see all of these levels are filled, right? And the last level is not full, so that is okay. But for the last level, all the nodes, whatever leaf nodes we have, they should be as left as possible, right? So here you can see that this node, this particular node, we only have one node in the last level, but it is not to the extreme left. It should have been like this here, right? It should have been here, but rather than that, like the filling for this last level should begin like this. We should first fill this child, then we should fill this, then we will fill this and so on, right? So all the nodes present here, they should be as left as possible. So here when I drawn these nodes, you can see that this has become a complete binary tree. That is, all the levels except for the last level are full, and if the last level is not full, all the nodes present should be as left as possible. So the filling is done from the left side, right? So I hope you have understood what complete binary tree is, right? So this question can be solved using both BFS and DFS, but in this video we're going to discuss the BFS approach, right? So see, we are kind of just dealing with the levels, right? We are talking about the first level, the second level, the third level, the fourth level, right? Now let's see how we'll be applying BFS here. So in BFS, what do we do, right? So we start from the root node. Then what do? We just push the the children of that root node, correct, inside of the queue. Yeah, first of all, we take queue data structure here, right? I forgot to tell you. Right, so what we'll be doing is, we will be, doing a BFS traversal, right? And we will just be adding one variable here to, we'll say, okay, right? This will be a bool variable and we'll say okay, and it will be initialized initially to false, right? Now what is the purpose of this variable? What this variable will do is, now let's see, one thing that we noticed here was, see, you have this and then, okay, wait, let's say we have something like this, right? So you can see when you will traverse it in level order way. So what do? You will push this node, right? Then you will push the left node and then this node. Let's name them, right? Just a minute. Okay, let me rub the board and then write again. What we'll do, see, we have this A node, then we have B node here, we have C node here, D and E, F and G. Okay, here we will not create, and here we will have our H node, right? Now what we are saying is, let's see. So first what we'll do, we'll put A here, then we will pop A out and we will put B first and then C, correct? Then we will pop B out, sorry, we will pop this out from here and we will push the children of B here. So first we will push D and then E, correct? And then similarly we'll do for C. So we will have F and G here, correct? And then we will pop D out and push H here, correct? I'll draw it here. So our cube will look like F, G, right? And we popped D out. So we will push, first see, we will be pushing its left child and then its right child, correct? So here what we'll be getting is, because D does not have a left child, so we'll be getting a null value here and we will be having H. Now see, if the tree is complete binary tree, then this null will never be present inside of the queue. Why? Because see, what we are doing is we are going from the root node and then we are pushing the left child first and then the right child. Then similarly for the left child, its left child is first pushed inside of the queue, correct? So if we encounter this null anywhere inside of the queue and we have have other nodes inside of the queue also, then we can easily say that, see, this null is present, that means a left child was empty, correct? There was no left child. So that means the tree that we are currently doing BFS traversal of is not complete binary tree, right? So this is the only logic, right? And this applies to such problems also when let's say this level was not full, correct? This level was not full. So what will happen here? Let's again draw the queue, correct? So this was the case when we, the queue that we just draw, it was the case when all the levels were filled, but the last level was empty, right? So then we can easily say that if null was present, then definitely this tree is not complete binary tree, right? But now let's say if all the levels are not full, then what will happen? We will, let's see, we will encounter the same case. How? First, we will be putting A here, right? We'll pop A out, then we will put B and C here, correct? Then we will move forward and we will pop out B and we will insert D and E here, correct? Then we will pop C out. Now see, what we'll be pushing? The null children of C, right? So inside of our queue, again we have gotten our null values, right? And then what you will do? You will take the D node, right? And you will push its children. You have the D node and you will push its children. So you will get null and an H. Now again see, we have another node here, right? After null. So you can say that, see, we have encountered a null here. That means it is not a complete binary tree because we still have other nodes to be traversed and null should not come first. Because if it is complete binary tree, then all of its level will be filled, and if the last level is not filled, then all the nodes should be filled from the left side, right? So that is how we'll be solving this using BFS. Now let's see the code, right? So here, see, first of all in BFS, what do we have? We have a queue. So we have created a queue, then we push the root inside of the queue, and then we have taken this bool value. Now whenever we encounter any node which is null, right? Any node which is null, then we will set this variable to true, right? Now see, here we are taking the first node out of the queue and we are checking if this is null, then we will set this to true, right? And then we will be pushing the children. Like if the current node is not null, then what we'll do, we will be pushing the children inside of the queue. Now see, we will be after we go inside of this condition, we will go again inside the queue, right? The queue is not empty, right? That is the condition. At this particular value, the queue will not be empty. So you will keep going and checking. So whenever if there is any node present after a null inside of the queue, then you have to return false, right? So here we first checked if whatever node we are traversing for, if it is null, then OK will be true. Then in the next iterations, what will happen? See here, we were at this position, correct? We were at this position. So we at this position we have set our OK to true, correct? Now we have other nodes also, right? We have other nodes also. Now if all the nodes after this are null, then we will not be going inside of this condition, inside of this else condition. So we will only go inside of else condition when we encounter a node which is not null, correct? So that is what we are doing here. So that is the condition. If there is null present before any other node which can still be traversed, right, then we should be returning false. Then we can say that the tree is not complete binary tree. So that is why we have put this condition here, and here only we can return false, because if we have encountered a null and we are at a node which is not null, that means the tree is not complete binary tree. So that is how we are checking. Otherwise we will return true. Like if this does not happen, like if we don't go inside of this particular condition, right, if we don't go, like, see, we can also have all values null here, right? Let's say if we didn't have this h here, correct? If we didn't have this h here, then what would happen is we'll never have any h inside of the queue. We'll be ending at null. Like null values will be inside of the queue, but we'll be ending at null only. And after this we will be we will pop out all of the values from the queue and we will return true, because in this case you can also see here in the diagram that this particular tree we have here is a complete binary tree. So we have first node, and then we have the second level filled, and the third level is not filled, but all the nodes are filled from the left side. So it is a complete binary tree. So in such cases we will simply return true. So that is how we have to solve this question.